Hess's law is our lesson today, and something you need to understand about enthalpy is that it is not dependent upon the reaction pathway. In other words, it doesn't matter how you get there, you just get there. So the example I've been using today to kind of help you understand this is raise your hand if you live in the forest of Friendswood. Several of us live there. Okay, how did you get to school today? Did you all come the exact same way to get to school? How do you get to school? The bus. And what? So the bus probably takes lots of winding roads, right? But you still ended up here, right? I mean, I'm assuming the bus doesn't take a direct path because they've got to stop and get a bunch of other kids. Andrew, how did you get to school today? What roads did you take? That's a lot of turns. Anybody else that left from the forest today, how'd you get here? You kind of left from the forest, or you did? The forest is not a rough area. It's a very nice area, actually. Okay, and how did you get to school?
I could show you, I could not tell you.
People, y'all are going to be driving someday. Pay attention to how you get places. Yes, I'll tell you that story later, how my husband made my oldest daughter cry one time because he wouldn't tell her how to get home. It's like, you got to figure it out. And so she started crying. So as you're riding around with your parents and you're learning to drive, pay attention. Okay, so my point is, we all left from, generally, well, I did, and I left from the hotel because we're still in the hotel. But generally, we left from the same vicinity, and we took several different directions, but we all ended up here. So it was independent of the pathway we took, we all ended up here. We all went from point A to point B, got there, but we kind of went different ways to get from point A to point B. And so enthalpy is the same way. There's different independent pathways, or the pathway, not independent pathways. It does not depend on the pathway to get your total enthalpy. So that's just kind of an example. If you can find the combination of chemical equations that add up to give you the desired overall equation, then you can also get your delta H for the overall equation. So, for instance, we took our different pathways. If we knew how much gas it took to go each one of those ways, we could figure out the total amount of gas that it took each one of us to get here. And it would be probably a little different depending on which way we went. Okay? So, when we're doing Hess's law, how many of you like puzzles? I love puzzles. If you like puzzles, you're going to like Hess's law because it's a puzzle. Okay? First of all, we have to decide how we're going to rearrange the equations. So you're going to get a series of equations that need to add up to your overall equation. So you're going to have to decide, how do I arrange these? Second of all, you're going to see if you have to reverse the equation, then you have to reverse the sign of delta H. We talked about that yesterday. If it's exothermic going one direction, I reverse it. Now it's an endothermic reaction to go the opposite direction. If I end up having to multiply my equation by an integer, or dividing my equation by an integer, I have to do the same thing to delta H. Okay? So in other words, if I need twice the equation, I would have to multiply my delta H by 2. Okay? Same thing for division. So best way to do it is just do some examples. Okay? So our first example is super easy. We're going from graphite carbon to diamond carbon. So we're looking for this overall equation. So we're going to take these other two equations and we're going to rearrange them and manipulate them to get them to add up to our overall equation. So the first thing that I notice about the first equation, so we'll call this equation 1 and equation 2. So equation 1 is already in the right direction because it's going from graphite to plus oxygen yielding CO2. So I've got graphite on the right side, which is actually not the right side, the left side, the correct side. So I'm not going to do anything with that. I'm going to leave it alone. But if I look at equation 2, I have diamond as a reactant, and my overall equation needs diamond as a product. So I'm going to reverse this equation. So now I want to rewrite everything. So I'm going to say C graphite, and I'm going to abbreviate, plus O2 is going to CO2. And my delta H value is a negative 394. Then I'm reversing this one, so it's going to be CO2 is going to carbon diamond plus O2. And because I reverse that, my negative 396 is now going to be a positive 396. So now I add everything up. If something appears on opposite sides of the equation, it cancels. Okay? So CO2 is going to cancel because it appears the same. Okay? What else is going to cancel? O2. So I'm going to cross that out. Then I'm going to rewrite it. Carbon graphite going to carbon diamond And then I'm going to add up these two values, which would give me a delta H of positive 2 kilojoules per mole. So for the equation of graphite turning into diamond, I would need to add 2 kilojoules of energy per mole to get it to happen.
Is it a lot?
Yes,
Why do we go to the diamond, not graphite?
because graphite's already on the reactant side, and that's where I need it. I'm trying to get it to match this equation.
Oh, okay.
Okay? Any questions on that? So if I wanted to reverse that, so graphite to diamond is what we call not thermodynamically favored based on its delta H value. Okay? So thermodynamics is going to tell us if something is thermodynamically favored or not. It doesn't tell us how fast. That's kinetics, which we do unit after next. Yeah, unit after next. Okay? So if I want a diamond to go to graphite, it would actually be an exothermic reaction, which is thermodynamically favored. But kinetically, it happens so slow that it's essentially a diamond is forever, because it's so slow. Okay? So let's do another one. Again, we're trying to get to this equation. So I'm going to look at, we're going to call this equation 1, equation 2. So right now, I look, and the first thing I see is NO is a reactant. And in equation 1, NO is a product. So what do I need to do? I'm going to reverse it. Okay? And then if I look at equation 2, I've got NO2 as a product. So I'm good. I'm going to leave it alone. Okay? So I'm going to rewrite these. So I'm going to have NO yields half of an N2. And when you're manipulating all this, if you want to leave out the states of matter, you can, because it's tedious. But in the overall equation, you should write the states of matter. But you need to be very careful, okay? Especially on your worksheet today, the very last equation, you've got aqueous aluminum chloride and you've got solid. So don't get confused and think you don't need to manipulate when one is aqueous and one is solid. So pay attention to that. Always, at least when you're looking at them, pay attention to your states of matter. The other thing that can get tricky with that is water, because a lot of times water is either liquid or gas. So pay attention and make sure you have the right state of matter for whatever you're looking at. Okay? So that's going to be plus half an O2. So we changed the sign. So we're going to say that's now a negative. And I'm just going to call that 90.3 for our math purposes. It's just easier. Okay? And then the second equation I left alone. We didn't do anything, so we just keep our regular delta H. So now let's change colors here. All right, I'm going to cross out my nitrogen. What about my oxygen? I have half here, so I can get rid of that, but now this one is going to become a half. For me personally, I just go ahead and circle it so I know I made that change, that that's not what it started as, so I don't get confused. Okay? Because if I wrote down a half there, in the same color, I might think I was supposed to cancel it after all. So if you do something like that and you leave something, go ahead and just circle it so you know, hey, I made that change. That's what it became after I canceled. So now I have NO plus half of an oxygen yields NO2. And my overall delta H would be, I add those two together. There you go. Now we're going to get 57.1 kilojoules per mole. And we're going to go back and we're going to say gas, gas, and gas for the final. Okay? Yes, ma'am?
This is probably a very stupid question, but how do you get half of oxygen?
No. So that's one of the things I meant to say in the last one. So this is the first time that we've truly seen integers or coefficients of fractions. It's completely allowable. Completely allowable. Okay? The reason being is the definition for the heat of formation, remember when I had y'all circle it and underline it, is that it forms 1 mole of compound. Okay? So oftentimes that means in order for it to form 1 mole of compound, we have to use half. Okay? Now, in most reactions when I do them, I am not just doing 1 molecule of oxygen, 1 molecule of hydrogen, and making 1 molecule of water, am I? How could I isolate that? I'm doing it in a big, huge amount. But we can break it down to the molecular level and figure out that. Okay? So fractions are totally allowable. We don't do that in the beginning because it would confuse you. And it would, the balancing could be all different, and then everybody's confused. But technically, if you look at, in the next equation, you're going to see water being made. And technically for delta H, it's half of an oxygen molecule. So basically it's one oxygen atom. But since it doesn't appear like that in nature, you do 1/2 O2. Okay. All right, so next one. And that is this one right here. So we're looking for this equation. And so I want you to see that don't be afraid of big numbers. Sometimes you have to multiply by big numbers. Okay? So in the case of this one, I call this equation 1, 2, 3. Equation 1, I only have 1 carbon on the reactant side, and I need 5. So I'm going to say times 5. In equation 2, I only have 1 hydrogen. How many do I need? 6. No,
Coefficients.
coefficients, yeah. Technically, I do need 12. But what do I need to multiply? By 6. And then if I look at the third equation, what do I need to do to it? Reverse it. Okay? So now let's rewrite everything. 5 carbon plus 5 oxygen yields 5 CO2. My delta H is now going to be 5 times negative 393.5. If you want to go ahead and multiply that and put it down, you can. I'm going to write it like this so you realize I have to multiply it by 5. So I don't just write down this big number and you're like, where did that come from? Then we have 6 hydrogen plus how many oxygen? 3 yields 6 water. So delta H is going to be 6 times negative 285.8. And then we're reversing that. So we have 5 CO2 plus 6 water yields C5H12 plus 8 oxygen. And that one, we need to make it positive because we reversed it. All right, let's cancel everything that we can. I can cancel the 5 CO2 right off the bat. What else can I cancel? I have 8 oxygen here, and I have 8 oxygen here, so I can cancel all of my oxygen. Anything else I can cancel? The 6 water. The water. So 5 carbon, which is a solid, plus 6 hydrogen, gas, yields C5H12, gas, which is pentane, in case you're interested. So I add all of that up, and I believe it's negative 145.7. Now on these, what does my sig figs need to match?
The smallest delta H. Decimal point?
Decimal point. Good job. You get it Starburst. Yeah, because we're adding here. We're not multiplying or dividing, so we got to match decimal points. Come grab a Starburst. Good job. Okay. Before we end the lesson, any questions?
Can you only cross out if it's on the other side?
On the opposite side. If it's on the same side, what should I do with it? No, add them together. So like if I had an oxygen here and an oxygen here, I would add them together. If they're on the same side, you add them up. If they're on opposite sides, they cancel. Yes?
They're going to be like a 3 like that, but 2 of them have carbon in them, and we have to try to like add them together, try to manipulate it like that.
That's what he just asked. Sometimes yes. Sometimes you might have to add them up.
And
Some of these can get actually really complicated. We did fairly easy, straightforward ones, but there's, and especially in AP Chem, some of them can be quite the little booger to figure out. Okay.
Miss Burke, one more question.